AI predictions are often black boxes. We see the output, but why does a complex convolutional neural network classify an image as a cat? The answer isn't in its final layer, it's in how it processed the input. To truly trust these systems, we need to visualize where in the input image the network looked to make its decision. This is precisely where class activation maps or CAMs provide profound insight. They highlight salient regions, crucial for a specific prediction. Grad-CAM, a powerful variant, goes deeper. It leverages the gradients flowing back from the target class prediction to the final convolutional layer. Think of it as backpropagating importance. These gradients are globally averaged, yielding neuron importance weights, essentially how much each feature map contributed to the decision. These weights are then linearly combined with the forward activation maps of that same layer. The result is a coarse yet powerful heat map, overlaid directly onto the input image. It visually articulates the regions most influential in the model's confidence for a particular class. By applying it to the last convolutional layer, Grad-CAM balances high-level semantic information with sufficient spatial resolution. This isn't theoretical, it's practical. In medical imaging, Grad-CAM helps identify tumor regions in X-rays or MRIs, aiding difficult diagnoses by showing clinicians where the AI sees anomalies. For autonomous vehicles, it confirms the model focuses on pedestrians and traffic signs, not just arbitrary background elements. Even in manufacturing quality control, it pinpoints subtle defects on a product surface that might otherwise be missed. Contrast this with simpler occlusion sensitivity methods. They iteratively mask parts of an image, computationally expensive and slow. Vanilla CAM, an earlier approach, required specific architectural modifications, specifically global average pooling, limiting its applicability across diverse network designs. Grad-CAM's strength lies in its model-agnostic nature. It works with virtually any CNN architecture without retraining, a significant advantage for existing deployed models. However, Grad-CAM heatmaps inherently operate at the lower resolution of the final convolutional layer's output. They might miss fine-grained details, or if not carefully interpreted, could highlight spurious correlations rather than true causal features. It tells us where the network looked, but not necessarily how or why that specific feature was deemed important. Advanced variants like Grad-CAM attempt to mitigate some of these spatial precision issues. But the core challenge of deciphering deeper causal reasoning remains. Ultimately, understanding why an AI arrives at a decision is paramount. It builds indispensable trust in critical applications, allowing us to debug biased or flawed models proactively. Python libraries such as TF-Keras for TensorFlow Keras or PyTorch Grad-CAM for PyTorch democratize this critical explainability, transforming opaque high-performance systems into interpretable, actionable intelligence.